Hello and welcome everyone. As mentioned, our topic for today's session is characteristic mode analysis in Feko. I'll start us off with a bit of an overview of the method and its benefits, and then we'll also look at one or two examples, also including a demonstration. So some motivation for the characteristic mode analysis. This method gives you a fundamental insight into the physics of a physical electromagnetic problem without having to consider specific excitations. This method is helpful, for example, in antenna design, where how you modify the shape can affect the performance, and also obviously where you place excitations and loads. The standard design process, in this case for an antenna, usually starts with looking at your design parameters, for example, your operating frequency, the required gain, input impedance or port performance, and also the physical constraints such as the size. You would then start with potentially literature study or apply some design rules to get an initial geometry. After analyzing that geometry, obviously to test its performance versus your required design parameters, you would proceed to modify that geometry iteratively to optimize that to the point where you can reach your specifications, obviously then hoping to have a final geometry that reaches those requirements. We start with design parameters, for example, for an antenna. We investigate potentially through a literature study to get an initial geometry. We can then analyze that geometry in tools such as Feko, and then we need to optimize that and modify it to be able to hopefully reach our final specifications through our final geometry. Where characteristic mode analysis comes in is you can use this method to analyze your initial geometry and actually obtain the modal currents and patterns that this structure can support. You can then use those through pattern and port synthesis to achieve your design goals much more easily. Obviously, you can then also do a final analysis to confirm that the expected performance is reached. So let's see how characteristic mode analysis is able to do this. Firstly, let's start with some background. So the method of characteristic mode analysis is the numerical calculation of a weighted set of orthogonal current modes that are supported by a conducting surface. These modes are similar to waveguide modes, the difference being that waveguide modes are the propagating modes in some contained environment, while characteristic modes are radiating modes in an open environment. This method was originally proposed by Garbas in the 1970s and later refined by Harrington and Mauch. You see a visualization of eigencurrent modes, for example, for a rectangular patch, where each mode is a different unique current distribution. Why would we want to calculate these current modes? This allows for a systematic and non-brute force design process. It also provides us with physical insights into the operating principles of our structure or our antenna, and it helps us to determine the resonating frequency of specific modes, which could then also help us to determine the optimal feeding arrangement to excite those specific modes. An example shown here from literature is how this method can be used to determine the optimum feed placement for a triangular patch antenna to obtain circular polarization. This method will give us the current distribution as well as the radiating performance for the circular mode. From those current distributions, we can then see where the optimal placement for a feed would be to achieve that mode and that required performance. The method itself, the characteristic modes are obtained by solving an eigenvalue equation that is derived from the method of moments impedance matrix. It's separated into the real and imaginary components, and the eigencurrents and the eigenvalues are extracted using this shape of the equation. Important to note again that this is independent of any excitation. It only depends on the physical shape and size of the geometry. So we basically obtain a set of current solutions that is natively or naturally supported by the structure without even considering potential excitations for them. Some terminology for the characteristic mode analysis. The characteristic currents as well as the resulting characteristic fields are the real orthogonal eigenvectors. So that's the solution of the generalized impedance matrix. So obviously these modal currents and the fields that they support or radiate are quite useful because they show the performance or the effect of each of these modes. And here you see again the first four modes for a simple patch structure with the current distributions as well as the radiating performance of these modes. Again, these are independent of any excitation. The eigenvalues are obtained again by solving that eigenvalue equation, and they provide some useful information specifically when we plot them over frequency. The magnitude of the eigenvalue is proportional to the reactive power, in this case, the magnitude of the real part. So the modes would resonate more effectively if this value tends towards 0. If the eigenvalue is positive at a specific frequency, that indicates that the specific mode is storing electric energy. If it's negative, at that frequency, it's magnetic energy being stored. And obviously, as mentioned, if it's 0, that mode is resonating at that frequency. So for example, here we can see that mode number 1 in this example resonates at a frequency of 2.4 gigahertz. Another useful value extracted from the eigenvalue is the modal significance. Here you can see how that is derived. The modal significance is a different way of visualizing the characteristic mode analysis result. And for the modal significance specifically, a value of 1 would indicate resonance. This would be in the case of a lossless structure. If there are some losses included, that value won't reach a value of 1. Here again, we see that for mode 1, the modal significance peaks at 1 at around 2.4 gigahertz. If we do want to consider excitations in our characteristic mode analysis, we are able to extract modal excitation and modal weighting coefficients. And this is useful when trying to synthesize the full wave solution from the characteristic mode analysis modes. The modal excitation coefficient is an indication of how well a specific source or excitation would excite each of the modes. The modal weighting coefficient then considers both the mode's own weighting as well as the excitation to give us the contribution of that mode to the total solution. So the total full wave solution that you could obtain with a method of moments solution would be given by the individual modal currents weighted by the modal weighting coefficient. So if we do want to consider a source, we can obtain how well that source would be able to excite our individual modes. It's also possible to define the modal input power, and that's an indication of what fraction of the power applied to the structure is going into each of the modes. Again, those modes are radiating. So in the lossless case, we should expect all the power to go into those individual modes and radiate. If losses are included in the model, and obviously some power will be lost in the individual modes as well. Here's just an illustration of the modal input power for a simple wire dipole antenna. So this is a half wavelength dipole. In the graph here, you can see the current distribution for the first three modes. So we've got the first mode, which has the typical half wavelength dipole current distribution with the peak in the middle. The second mode, a higher order mode, has got 2 peaks, and the third mode, in this case, it's got 3 peaks over the wire. In this case, at the specific frequency, the first mode is dominant, and we can see that the current distribution for the total solution is very similar to the first mode's current distribution. Also looking at the modal input power, we can see that virtually all the power goes into that first mode. Looking at the characteristic mode analysis implementation and workflow in Feko, this method is quite simple to apply. We start by building or importing our required structure. So this could be an antenna structure. It could be a large platform if we're looking at using the method for antenna placement or scattering analysis. It's not required to add any ports or excitations. You simply create a characteristic mode analysis configuration where you set the number of modes you want to calculate. There's an option to compute the modal excitation coefficients when sources are present. That option you can use depending on your application. Next, you define the frequency of interest and then also request all additional quantities you might want to see, for example, scattered fields, radiated fields, and currents. Obviously, these will then be the currents and fields for the individual modes being calculated. The visualization options for the results. All of these results can be visualized in our post-processing tool, PostFeco. So on 3D graphs, you're able to see currents and charges, near fields and far fields for each of the modes. On 2D graphs, obviously all of those quantities, as well as the characteristic mode analysis parameters, such as the eigenvalues, characteristic angles, modal significance, and many more. It is also possible through scripting to implement modal synthesis automatically, where you can then combine weighted combinations of modes to achieve a certain performance. Looking at a small example of a mobile phone antenna analysis using characteristic mode analysis, the CMA offers you the ability to gain some fast insight into the fundamental resonant behavior of the different components of a structure such as a mobile phone, including the ground plane, the glass cover, the battery pack, and many more. We could, for example, consider the effect of a feed structure on the ground plane. Here you see the comparison between the ground plane's characteristic mode analysis without an excitation. That's at the bottom, and here we see that this ground plane supports various current modes, with the first and most dominant mode being visualized here in J1. We can, in this case, test a specific antenna and see that that antenna is able to very well excite that first order mode. This is based on the reference shown here. Another use case is looking at how we could potentially modify that ground plane without affecting its radiating performance. So if our intention is, for example, to excite mode 1, we can see that that mode has got a low current area in the middle here. So in some practical example, we might want to place a hole somewhere in our ground plane, for example, to have wires or other components pass through it. And this would show us that that is a good area for placing that hole, as it would not significantly affect the current distribution of the mode we want to excite for irradiation. And here you can see the comparison between the ground plane with and without the hole, with very little change in the excitation of those modes. The CMA can also be used to identify the modal components of a structure and then select the mode with the most beneficial performance. We can then try to excite that specific mode. So for example, in this case where we've got a metallic frame surrounding the device, we can look at the current distribution and the radiation performance of each of the modes and identify the one with the most beneficial or desired behavior. In this example, we consider the mode number 6 as the most beneficial one, and we can then aim to try to excite that mode in the structure to obtain that physical performance. So based on some specific placement or design of our feed element, we could extract the modal weighting coefficients to see how well that is exciting our desired mode. In this case, we can see mode 6 is well excited by our specific feed, which should lead to a performance, a total performance very similar to the mode 6 performance. And here we can confirm that with this specific element exciting the structure, the full wave solution obtained by the method of moments is very similar to the mode 6 performance, indicating again that we have excited mode 6 very efficiently. A next example, looking at characteristic mode analysis for antenna placement on an aircraft. In this case, we're looking at the HF bands, where the antennas on an aircraft would obviously be relatively small relative to the wavelength. These antennas will be difficult to match because of their small size, but we can use the insights from characteristic mode analysis to excite the whole aircraft as our radiating structure. We can then also attempt to excite multiple modes to obtain the optimal horizontal pattern. So let's do that live. So I'll switch to CAD Feko. So we start in our CAD Feko model with the aircraft geometry. In this case, this was imported. In the default CAD Feko session, we've got a standard configuration, which would be a method of moment solution, but we add a characteristic mode configuration. In this case, I'm only going to request 4 modes, as I won't have any excitation. I'll unselect the option to compute the modal excitation coefficients, and I'll create that configuration. Next, I only need to set my frequency. So in this example, let's go for linearly spaced points between 7 megahertz and 11 megahertz with 250 kilohertz steps. As soon as I do that, we should see that a mesh is being generated. Our next step is simply to request the parameters that we want to see. So we'll go for the full 3D far field pattern, as well as the currents for these modes we will be calculating. And there our model is ready and set up to run for the characteristic mode analysis. Again, we don't need sources, as this method is calculating those modes independent of the excitation. So let's switch to our post-Feko session to see those results from one I completed earlier. Okay, here we see our aircraft model, and what I'm showing you here is the modal currents at 9 megahertz. So that's for mode 1. I can switch to instantaneous to show you the direction of these currents. What we're seeing is that mode 1 has got the largest currents along the length of the fuselage, with the currents flowing, in this case, from the tail to the nose section. Let's see how the radiation pattern looks for that mode. As expected, this mode has got a dipole type pattern with the along the length of this aircraft. Let's see how mode 2 looks. I'll just switch the mode index to 2. For mode 2, we see the strongest currents are on the wings, and they're flowing along the length of the wings. Again, we'll expect this mode to have a dipole type pattern, but now orientated along the wings. You can see that clearly. Finally, let's see how mode 3 looks. So the current distribution for mode 3 is slightly different. Here we've got the currents flowing from the nose to the center, and from nose to the center, from the tail to the center, and then out along the wings in both directions. This should give us a bit more of a complex pattern. Let's see how mode 3 looks. And yes, clearly we see these four peaks in the pattern. Now that we have these, the behavior of these modes and how they radiate, we can start looking at how we could potentially excite a combination of these modes to give us our desired radiation pattern. Firstly, let's look at the modal significance. So this is the indication of how well these modes, or how significant these modes are in the solution. And this we plot over frequency. We can see here mode 1 peaks at about 8 megahertz. Let me add mode 2. This peaks at 9. Mode 3 with a sharper peak at around 9.75 megahertz. I've also included a fourth mode, mode 4. We can see clearly this one is much less significant, so we'll probably focus our attention in this example to the first 3 modes. If we were to start, for example, here I have the horizontal performance of mode 1, mode 2, and mode 3. For mode 1, we see a null in the forward direction, so we don't specifically want that. Again, mode 2 has got nulls along the length of the wings. Mode 3 has got these multiple nulls, so clearly we want a combination of that. How we can achieve that and how we should excite these antenna, this structure is guided by the current distribution. So let's, for example, have a look at mode 1 again. See mode 1 has got very high currents here on the tail section where it attaches to the fuselage. So that's probably a good point to place an antenna or an element that would excite the structure. We also have high currents here where the wings attach to the fuselage. So maybe those are good points. Let's just confirm for mode 2. Mode 2 similarly has got high currents here where the wings attached to the fuselage. So this is looking more and more promising as a placement for our antennas. We can confirm mode 3 the same, even though the currents have got different phasing and orientations. They are high in these 3 locations. So here I have an example where we placed some notch antennas in these locations. You have 1, 2, 3 of those. Now, depending on the orientation of these currents, we can use different phasings on these antennas to achieve the different modes. So for example, if I were to phase the 2 antennas here on the sides of the fuselage connected to the wing out of phase, I would probably excite this mode 3. If I were to excite them in phase, I could excite mode 2 with the currents flowing in phase. Also then possible to tweak those phases and have a different combination of phases where they are either in phase or slightly out of phase to achieve a combination of the modes. And in our example here, we had them 45 degrees out of phase, and I can show you the end result of that is this blue trace. So it should be that by combining those 3 antennas and phasing them to excite a combination of the 3 modes, we are able to achieve a radiation pattern that's got a strong radiation in the forward direction. Okay, so quickly to conclude, we showed the workflow for characteristic mode analysis in Feko. We showed how this method can give you insights that you wouldn't otherwise be able to obtain, and that this method enables you to pinpoint the optimum placement for a feed for an antenna structure, but also for the placement of antennas on a larger structure. And this method allows you to synthesize the desired pattern by exciting a combination of modes to achieve your desired performance. Thank you. That brings me to the end of my presentation.